right. So maybe introduce you in between. So in between your connect. Yeah. So Nicolas joined Zoom. Is almost there. It's a great pleasure to have Nicolas Thome visiting us this week. Nicolas was also participating to a summer school here at the ETS. Nicolas is full professor at the University of Sorbonne, affiliated to ISI, ici, which is a large seniors lab in machine learning and robotics, and with several fields of applications, including NLP and computer vision. In Paris, Nicolas has been working in the area of machine learning, in connection with deep learning for understanding low-level signals, computer vision, time series, interactions with robotics. He's mostly interested these days in robustness in AI, multi-modal models for autonomous agents, and physics-informed machine learning, which is related to also some work that Ricard presented before. So we will just check that you can hear us on Zoom. I just mute myself and I'll let Nico now to start.
J'arrive pas là dans Zoom. Non, c'est pas. Ouais, c'est cool. Pas changer d'écran.
C'est quoi, Nicolas, là? Je connectais,
ouais, mais la barre sur le côté.
Ouais, ben c'est ça.
Je sais, mais je pense. Si, mais il faut que je le fasse là. J'arrive pas là. Ok.
C'est ça. Bon, c'est bon. Ça ne gêne pas.
Ah, ça ne gêne pas. On va le mettre un peu plus haut. Hop.
Vérifie juste que ton micro n'est pas muté.
No, it should be fine. Just can you hear me on Zoom? Remotely?
Yeah, we can hear you.
Oh, no. Can you hear me online remotely? Yeah. Okay, fine.
Yes, we can hear you.
So thank you very much for the invitation. So we start. So today, as Pablo introduced me, I'm working at the Sorbonne University in the robotics lab, and today I am gonna present you some of my recent work about safety and robustness in AI and machine learning in particular. Ça marchait tout à l'heure.
C'est souvent plusieurs.
Okay. Great. So first, a very short introduction. So as you may all know, we are now witnesses for in the last decade a huge success of AI and machine learning in particular. And so there have been several huge models trained from various input sources that had huge successes. And as you all know, for what the very recent success in natural language processing with all these large language model and ChatGPT, and that show very big successes and that make very huge progress because of the pre-training of very large model, and that can tackle a large variety of downstream tasks afterwards. And there was the same kind of foundation model or vision transformer that have been applied to images. We have also this foundation model for that mix text and low-level inputs such as images. For example, clip is a very standard tool nowadays for mixing text and languages, and there are an increasing number of foundation models in various domains. For example, in robotics, as shown here on how recently related to the previous talk of Ricard, there have been also very recently foundation model on audio and speech as well. So, okay. The point is, okay, all this framework have made a big progress in the field. Okay. And what I'm gonna focus my talk today is about the safety aspect of the deployment of such model, and especially the robustness of such a model. And it is well known that all these deep learning models that are very expressive and that can model very complex dependencies between input and output also suffer from brittleness, and there are several aspects of this brittleness in deep learning. So I won't talk, of course, in all of them. You have issue about explainability, biases in dataset, shortcut that the model can learn, fairness, and so on. But I'm gonna focus today on 3 aspects related to robustness. So the first one is related to the stability of the decision function that we have. So it is well known that, as I said, the decision function, which might be very complex, that might represent very complex dependency, also can be very unstable. And for example, adversarial example is an example of that. You might have very small changes in your input that induce a very large variation in your decision. And you may also have a problem about dealing with mistake severity. That's something I'm gonna detail later on. Here is an example for, in an image retrieval context. You have a query image, and you want to retrieve similar image in a bank of image, and then you would like to retrieve the specific instance that you are looking at. For example, this bear here, and imagine you have this system that retrieve you correct sample or correct instances from the bear, but also make some mistake. You may want to penalize your system differently if it retrieves something that is not this specific bear, but for example, still an instance from the bear species, and you would like to score that better than if we would retrieve animals from completely different species, as shown in red here. So, okay, we would like to account specifically for this mistake severity such that you can control the error that your system make. So this is one point. The second point is uncertainty quantification in general. So uncertainty quantification is one of the major problems in AI and machine learning in particular. And one of the main objectives in UQ is to endow models to the ability to know when they don't know, to be able to perform some reject predictions. So once you train your model during inference, you would like your model to be able to output a confidence measure of your prediction. If it is below some predefined threshold, then you will reject it and do something. So, for example, ask for a human to do the prediction, or in medical context, you can do you can acquire another devices to make your input data more accurate. Okay, your uncertainty quantification in deep learning is a challenge. We have several open questions. What kind of uncertainty or confidence score should we use? How to get calibrated prediction, or how to rank properly your correct prediction with respect to your incorrect ones. And finally, the last aspect dealing with robustness and safety I'm going to talk about deals with direct optimization of target metrics. So in general, we train the most common loss function that are used in deep learning are classification losses based on cross-entropy or regression losses. But in several contexts, you may have a specific target metrics that you want to optimize and that are not directly optimized. For example, for image retrieval, where you have very imbalanced data, you are looking for a given query and there are very few samples from your query in the data set. Then the standard evaluation metric for the task are ROC curve or average precision curve, and we may want to optimize these losses. And there are two issues with these losses. So this rank loss in general that also occur in several other contexts. The first one is that those losses are non-differentiable. as would, for example, be the standard accuracy in classification. But for accuracy, we have good surrogates for that are used for training our models, such as cross entropy or hinge loss, and etc. And the point is, can we also design good proxy for good smooth surrogate for these rank losses that are nice theoretical properties. So this is one point, non-differentiability for those rank losses, and another more specific point that has a big impact when we train a deep learning model on batches is that those losses also are non-decomposable across batches, in the sense that those are list-wise batch. When you compute the rank, you cannot naively decompose the loss into batches as a sum of loss into those batches. And that's what is shown here. Here you have a list of examples. Here. Oh, this one, sorry. So you have this batch, you have a given query, and here the positive sample are shown in green, and the example which are relevant to the query are shown in green, and those that are irrelevant are shown in red. And you have the average precision, a very popular ranking metric, which is shown here. And if you compute the average precision on the full list of sample, it does not match the average precision that you would have on here the three batches shown below. Okay, just to illustrate why in this example it is not naively decomposable into this linear this sum of the loss over batches. And this is something that occurs in other contexts, that in rank losses, for example, many other losses such as segmentation lists are not decomposable either. Okay, and I will present some of my recent work to improve on these three directions. So the first one is about uncertainty quantification, and I will present some of my recent contribution to improve the quantification of uncertainty along the two main sources of uncertainty that we have. So the first source of uncertainty that we may have to deal with is aleatoric uncertainty. So aleatoric uncertainty is something that is inherent to your data. So you have data that may be ambiguous, and that what is shown here, for example, imagine that you want to segment this medical scan, and that you want to segment this region close to the blue cross, sorry, which is a pixel from the pancreas. When you look at this region, the contrast is very low, and then it's very challenging to segment it. And then it's an example of only based on the luminance itself locally, you cannot segment it, and you have to rely on something else, and then you have a large aleatoric uncertainty. Okay, this is the case in other contexts. For example, this is very common in autonomous vehicle. If you have sun glare, rains, and so on, you have your data are corrupted, and then it becomes very challenging to perform your task, and you have a large aleatoric uncertainty. So this aleatoric uncertainty cannot be reduced, but the goal is to be able to estimate it. Okay. And epistemic uncertainty, in the other hand, it's related to some shift that you may have between the training data that have been used to train a model and the testing data that where you apply your model during inference. For example, if you train a segmentation model in autonomous driving and you've never seen an image with snow, then it will be very challenging. So here is an example of shift that you have in your inputs, in your image, in your input X. It can be the same if you train your model for recognizing natural images and you want to apply it on sketches. And it can also it can also occur because you have some shift in your output in the classes. For example, if you want to deploy your autonomous system with this kind of tuk-tuk vehicle that never occur in Europe, for example, it might be a challenge because you've never seen such class in your train set. Okay. And so what is a very naive baseline for classification? If you deal with classification, a very naive baseline to estimate the model uncertainty is to use what we call the what we call the maximum class probability. So you have your model. So you have an image, for example, or whatever you want. You have a pre-trained model, your favorite model, a convnet, or your favorite transformers. As you are dealing with classification, at some point at the end, it output a probabilities over class, and it has been trained with cross-entropy loss and softmax function. And then your prediction consists in taking the class with the largest probability. And then baseline, naive baseline for uncertainty quantification consists in taking the probability associated to the maximum class. Okay. And it turns out that if you do that, and if you use that metric, that criterion for failure prediction, so for identifying for a given pre-trained model, if we are able to distinguish is correct from incorrect prediction, then it will not work very well. And that's what's shown here on the left-hand side. So these are real confidence score obtained from a pre-trained convnet model on Cypher10. And here, what we can see is that the histogram of confidence that you get with this MCP value, there is a large overlap between your misclassification in red, so your wrong prediction, and the correct prediction that you get in green. Okay. And so we try to do better. And the idea that we had is that, of course, by design, this maximum class probability, it gives you very large score for incorrect prediction, because by design, you compute the max over probabilities. So what if instead of using this maximum class probability, you would use the probabilities for each sample associated to the ground truth class, which is denoted here as TCP, true class probability. And it turns out that if you use that, you most of the case almost get a perfect separation between your errors, your misclassification, and your correct prediction. And that's what is shown here on the right-hand side. If you use that criterion, it's a much better suited criterion for this problem of failure prediction. Okay, so how to use it in practice? Because of course, TCP requires to have access to the ground truth class, and of course, you don't have access to the ground truth class in France, otherwise you won't have any prediction problem. So the basic idea here in this work was to start from a pre-trained model on some data set and to train another model, the confidence network. So the first model, the prediction model that is given to you is this blue model. And then we will train a second model, second network, which is this confidence network shown in orange here. And the job of this second network would be to predict the confidence of the model, and to train it, we will try to predict this TCP criterion from this blue network. So for each sample in the training data set, you are able to compute the probability associated to the ground truth class in your train set, because you get those labeled data. And then you optimize the parameter of the second network such that it outputs you the value of this TCP, which is denoted as C star here. And then you optimize this W parameter such that you have a very small confidence error on your train set. Okay, so pretty simple idea. And it turns out that it works pretty well in practice. So those are some experiments that have been carried out in standard simple classification dataset, MNIST, SVHN, or Cypher, and also a segmentation dataset here, Cambid, where we apply the same idea at the pixel level with a segmentation network. Okay, and we can see that we have some consistent improvement compared to this MCP baseline, and also to Bayesian method, Monte Carlo dropout method, or compared to other methods, for example, this trust score approach, which is specifically designed for misclassification detection. Okay. We also extended the idea in two directions, especially to deal with segmentation. The first one was to apply this uncertainty quantification based on learning model confidence for domain adaptation. And so in unsupervised domain adaptation, the context is that you have a source domain. So you have images with segmentation mask in your source domain, and you want to apply your model on a target domain where you don't have any labels. And state-of-the-art model at that time were based on using pseudo-label from the model trained from the source domain. So you have a model which is trained on your source. Then you apply the model trained on your source on your target domain, and it gives you some prediction. And the idea is to use the most confident pixel predicted on the target domain as pseudo-labels to fine-tune your model. And here, what we did is that specifically to use this uncertainty metric as a way to select the most confident pixel in the target domain. Okay, we show that it worked better, of course, than using more naive uncertainty quantification method. Okay, the second extension is an application for medical image segmentation, which is somehow not exactly the same context, but it's closely connected. Here we have a semi-supervised method, and again, the goal is semi-supervised method in the sense that we train a model with, let's say, few labeled samples, and we want to also leverage unlabeled data. And again, here we will use the model to we will use our prediction model and use it to produce pseudo labels. And again, we will use the most confident pixels prediction to serve you as a target and fine-tune the model later on. So here it was done in an iterative manner. So let's say in a curriculum-like manner, where you first apply your model on some unlabeled data. You select a given ratio of the most confident pixels. You retrain it, and then you gradually increase the number of pixels that you incorporate for fine-tuning your model. Okay, and so it helps to improve the performance. And here on this bottom figure, what we show again is that the confidence estimate that we get. So here is a zoom of the pancreas zone. Here, when you have correct prediction of your model shown in green or cyan and error shown in red. And what we see here is an uncertainty map that you get if you use this MCP baseline, or if you use the learned confidence that we use with our model. And what we observe in practice is that this MCP baseline is somehow fires or give you large uncertainties, essentially at the organ boundaries. That is not very interesting, and that in contrast with our method, we are able to have large uncertainties in areas where the model fails. Okay. Right. So this was more targeted. So this was this first line of work were more targeted to the first source of uncertainty, aleatoric uncertainty, because we were looking for a way for a model to detect their own mistakes, right? And so, okay, I also contributed for improving the quantification of epistemic uncertainty for out-of-distribution detection. So in out-of-distribution detection, you want an uncertainty metric, which is able to tell you if your data is belong to the training distribution your model has been trained on or not. And if it's an out-of-distribution sample, you want your model to abstain to make any prediction because you don't know what to predict. Okay. And so we are in a context where we want to apply OD detection in a post-hoc manner, in the sense that you get, again, a pre-trained prediction model, classification model, for example, where you don't want to retrain it because it might be a very large model, for example, a very large foundation model. And in this context, a state-of-the-art model for out-of-distribution detection, what they are doing is that they try to learn the densities of your pre-trained model in some latent space. Okay, you have a pre-trained model. For your in-distribution sample, you are able to extract some latent representation from your in-distribution samples. And the idea is to try the density of your in-distribution samples. And then based on this density estimation, you are able to give a likelihood for a new sample at test time during inference to decide if it's an in-distribution of or out-of-distribution sample. Okay. And so state-of-the-art model, they are based on using simple model for this density estimation task in the latent space of those models. For example, using a Gaussian mixture model or using the energy logit of the classifier. Okay, and the idea in this work was to improve this work at two main levels. So the first one is to start from those simple density model, such as Gaussian model, for example, but to try to correct them because they might be not very accurate to describe the density of data. So to add another network to refine the density estimation of this prior model, this prior density Gaussian models. And a second improvement based on being able to combine different sources for estimating the density estimation to leverage different models. For example, Gaussian mixture model, which are by design, they are based on Gaussian density. So those models by design will give you a very low density if you have models that are very far away from your training data. And so, for example, those models are known to be good to detect what we call far OOD samples. So if you have an OOD that doesn't look like at all compared to your in-distribution data, it will by design give you a very low score. On the other hand, it might be less accurate to detect OOD that are closer to your input data. And that somehow the contrary that can be observed with energy logit, which is more based on the discrimination features of your logit, and in general it works better for near OOD samples. Okay, and so what did we do in practice? So the method works as follows: you have your image. You have phi, which is the embedding of your pre-trained classification model. So this is given to you. You have a pre-trained classification model. It will map your input X to some latent vector Z. And then you want to learn some density in this latent space. And the density, to model the density, we leverage an energy-based model, energy-based framework, where the density is cast, the density estimation is cast consists in estimating the energy in this energy-based framework. And then in this energy, we consider two terms in this energy-based model. So a prior energy function that might, for example, be a Gaussian, simple parametric model. So I've shown below a Gaussian, for example, and we learn some residual energy-based model to correct it, to have some residual energy term that can refine this prior density that might not be as accurate as we want in practice. Okay, and we can use several prior, this Gaussian density prior or another prior that, for example, comes from this energy logit term and so on. And so, and at the end, we were able to have our final decision, our final density estimation, to combine these different energy terms, to fuse them and to have a decision based of more diverse sources to perform density estimation. Okay, and so that's some experiment that we did where we compared. So this method, it was our method that we compared to several recent baselines. So method based on energy logit, SSD was method based on Gaussian mixture model, and other method based on nearest neighbor and so on. And we observe that we get better result at that time on different data sets. So we experimented on Cypher, but also on larger scale data sets such as ImageNet. So okay, that was for this, let's say, OOD detection, which was contribution for epistemic uncertainty qualification. Yeah.
It's okay to interrupt that. It's okay.
Yeah.
Question is like, why evaluate on this performance measure? Is this false positive or this performance measure you have on?
Here it's a standard metric. It's a false positive rate at 95% accuracy. It's a standard. It's really at the end what you do. You have a binary prediction problem. You want to distinguish in from out of distribution samples, and generally performances are evaluated using a ROC, AUC, or this FPR metric.
you think it gives a good, like, is it a good performance metric, you think, for, like, it seems like it, on the surface, I don't know the area, but on the surface, it seems like incomplete in some ways, or like it doesn't measure, let's say, the impact of if you have imbalance or if you have,
yes, I would say it does, but yeah, I think the point is that you trace all at 95% accuracy, so it's not so. This trace all give you something, but for example,
you
yeah,
catch the imbalance. You catch the imbalance.
Yeah, you
the
can.
arrow, no, but this one it does.
Yeah, so yeah, IUC rock, you might also catch imbalance. So if you have average precision, it's really targeted to imbalance data when you have average precision. IUC rock, so yeah, you can symmetrize it, so it's not dedicated to the error, but yeah, this metric also catch imbalance.
May I have the chance to ask, do you know what have you tried to, for example, if the in-training data was cipher 10 and the out-distribution data was cipher 100, so which is this near out-distribution case? Well, do you have the performance there? How this? That's one of the tricky cases in which all the performance are bad. So that's why I ask you, because it's so clear.
I don't have the result there, but it's on the paper. I can show you, especially that's something that we wanted to be good jointly for near OOD detection and far OOD detection. As I was mentioning, generally all this density, Gaussian density, they are good at far density estimation, but bad at near and and so we were good at both. And that's the standard setting where you train on cipher 10 and you evaluate on several near, mid, and far OOD samples. Yeah.
So the data is imbalanced at test time as well,
or? I'm not sure on the exact protocol. I'm not sure it's in balance. So you have your in distribution sample, but I guess it's somehow you add some OD from another data set, and I'm not sure it's in balance. I have to check.
Like I think probably I mean it's one challenge. I don't know about this area, but you know, often people will train on imbalanced data or balance their data for training.
Yeah.
But then there's no way of knowing in test time what the imbalance is.
Yeah.
Right. So I guess you can have different losses that can help, but in general, it's
I think
it's like a hard case, you know, because like in practice, you know, you could get a data set and do a great job of training, but then often the training set doesn't necessarily correspond to the test set. And you could have different levels of balance that you don't know about.
Yeah, here the imbalance is really the ratio that you have in between in distribution sample and OOD samples. Here, I guess it's in this experimental setting, it's balanced. It really depends. So I don't know if it's representative of real scenario. It really depends on the applicative scenario that you have at the end. So the ratio that you have between OOD samples and in distribution samples really depend on what you have. For example, if you want, you have your autonomous driving system for segmentation, you might have some ODs, but the ODs can be very rare in some cases, but still occur. So it's really task dependent, I think.
Yeah, thanks.
Okay, so this part was to try to improve the detection, the quantification of epistemic uncertainty, and the last work I'm presenting here is about robustness in prompt learning, so more recent method for few-shot learning. So in this prompt learning method, what we do is that we start from a pre-trained foundation model. For example, clip here, you have an image, you have a pre-trained vision encoder, you have a pre-trained text encoder. And in prompt learning, instead of using clip in a zero-shot manner with some prompts, this is an image of class, blah, blah, blah. You try to learn the different elements of the prompt using learned embedding. And that's how you adapt your foundation model to your downstream tasks. And so the goal really is to have this learnable prompt with few parameters that can be easily trained and that generalize well to few shot to this few shot context. And here, what we wanted to do is to have this learnable prompt and be able to have prompts that align with some local image region. So we have to have this, what we call local prompt. We have a prompt that can fire on some specific element of the object, the concept, etc. So a first observation is using this the vanilla clip for that does not work well for this local prompt, but what we show here, because and this is somehow expected, because during the clip pre-training you only align your global representation from the image with the global representation for the text. So there is no training signal in clip that encourages to have an alignment between some text, global text, and your local region. And that's what is shown here. If you use the local features from clip, it does not work well. It does not align well with your text, with your concept. Okay. So it was first limitation that we want to overcome, and another limitation is that most of the prompt learning method that exists in the literature that try to improve accuracy, then most of the time it's done at the cost of robustness, and especially the method that performs the well in accuracy. That's what we shown here. So accuracy here is shown in the x-axis, and we show that the best method for accuracy, they are generally not as good for OOD detection, again this FPR metric, and not as good for domain generalization where you apply some perturbation to input and you evaluate the performance that you get afterwards. Okay, and that was the motivation for this approach, to jointly try to include local prompts, prompt that can fire in local region, and a method that can be good, that can have good accuracy performance, but also good domain generalization performances and out of distribution detection. And that's what we did in this approach, so in this Gallo framework for learning global and local prompts. And so there is a first, so for the local prompt, there is explicitly in this method an alignment of the vision encoder and an explicit selection of a local subset of region that we have in the image. So for example, we compute the alignment using a standard clip alignment method between the text encoder that comes from the learnable prompt. You have learnable prompt, and then it gives you an encoder from your text encoder. And then the alignment that you get, we enforce the alignment to be localized. So we only compute the top K largest similarity in this local region, and then it enforces to have a linear alignment. And we also add here a trainable linear layer, because we wanted to improve the alignment of local feature from clip, but is not observed from the pre-trained clip, because it is not enforced during the clip pre-training. And so this is what we did for this local prompt. And so we combine this local prompt that align with some local region and standard global prompt. And here for global prompt, what we did is that we include some diversity in the prompt that we learned using some variant of dropout during training this global prompt. So an application of dropout at the level of the prompt. Because the idea is to output a set of diverse prompts that can capture different aspects of your training problem. Okay, and so yeah, but I think I already commented that. So it's just a more detail about how we compute this sparse alignment. So we simply have the embedding from the prompt, the local prompt. We compute the similarity, simply the dot product between this prompt and each local region, and we select the top K similarity with respect to this similarity measure. And we had, before computing the similarity, this linear layer that help to refine the local feature to be more aligned with.
Quick question. So what are the local features look like? Do you like go back to a previous layer, or?
Yeah, just the layer before the last layer of the clip transformer, just before the CLS token that it feels.
Got it.
Yeah. And yeah, again, here to include diversity, we have this prompt dropout, which consists in just dropping some random sample in the batch that we have at the level of the prompt. And for the local feature, we also add a multi-scale loss. So just varying the number of K that we use to compute this top K assignment to have a multi-scale local prompt and to add more diversity in the prompt that you have by this way. Okay, so we show that it works well. It works better than the baseline, of course. And what was interesting here, so when we look at this Gallo method, is that we have good performance for the global prompt. So here is the performance that we get on some data set here on Cypher 10, I guess. But you have good performance from your global prompt, but also good performance from your local prompt. But what was very interesting, because if you use the vanilla kit, it's not good at all. But even if you use more advanced prompt learning method, the local variant of those methods are not good for in terms of accuracy. Okay, so we managed to get both, so good accuracy both for global and local prompt, and then we were able, by combining them, to improve the overall performance at the end. Okay, and also the point was that we were good in domain generalization, so this column, and in OOD detection. So these two metrics is FPR 95 and also IUC, which was this OOD detection, the second OOD detection metric. Okay, so this was for uncertainty quantification. So the first element of this robustness part. Then I will switch to the second part for designing method for direct optimization of rank losses. So the contribution that we made here, it was a method dedicated to try to directly optimize during training some non-differentiable and non-decomposable rank losses, as I was mentioning. For example, the most popular one is average precision, that is used to evaluate the model at test time. And so we try to design a smooth surrogate of this average precision metric that has some theoretical properties. So I will give you more detail just soon. And also to propose a method that try to reduce the decomposability gap. So the decomposability gap is the loss that you gain, or the metric that you get on the whole training set, on the whole list, compared to the average loss or the average metric that you get across batches. So we wanted to design a method that can decrease this gap between batch loss and overall and list-wise loss, such that when you train your model with batches, with the standard way, with stochastic gradient descent, you have a better approximation of the list-wise loss that you would have initially. Okay, so we are in this context, we apply the framework to an image retrieval setting. So you have a set of images, and you have some queries, and you want to retrieve similar images with respect to this query. So that's the task. And to do that, you have some network, again, your favorite network, your convolutional or transformer model, which transform this input into a latent space. And then what we do then is that we want that the relevant image with relevant images with respect to the query, they are closer than the irrelevant ones. Okay. And to do that, then we introduce a smooth relaxation of the average precision loss based on a smooth relaxation of the rank function that is probably an upper bound of that gives you an upper bound surrogate of your average precision. So it has nice properties. So very shortly, just to give you to position you to position our work with respect to what is done in the literature. So trying to have a smooth surrogate from rank losses is a very old problem. And so basically, here I give you 3 classes of method to do that. So the first one is to have, let's say, standard losses or naive losses, such as triplet losses, for example, which are commonly used in metric learning and image retrieval. But the main drawback of those methods is that in general, those methods, they provide only a very coarse upper bound of your average precision loss. So they do not provide accurate approximation of the loss. And they generally, and also an important drawback is that they do not support in average precision. You want to more penalize errors that are at the top of the list compared to errors that occur at the bottom of the list. And triplet losses, for example, they do not reflect that at all. Okay. This is one point. So there have been also methods that try to explicitly design upper bound of these rank losses. For example, that's what has been done in all these structured output prediction models, structural SVM, where you explicitly have an upper bound of your loss function. Or in more recent black box optimization method. And so when you do that in general, so the good point is that you get theoretical guarantees and you get an upper bound of your loss, but you still get a very coarse approximation of the loss by using this method. And finally, there have been more recent approaches that have been trying to compute or to approximate the rank function, because all these matrix, average precision, and other rank function, they are based on the rank function. So in general, this kind of method, for example, the smooth IP, it gives more tighter approximation of the final loss that we have, but in general, you don't have any theoretical guarantees that you have an upper bound on your matrix. Okay, so this was for state-of-the-art method for designing smooth surrogate of this loss. And so there has been a lot of work on that. But on the other hand, there have been much fewer works on trying to deal with this non-decomposability issue. Okay, so there are much fewer works that deal with that. And generally, the method that deal with that, they are, let's say, brute force approach, in the sense that to deal with that, with this non-decomposability, either the method relies on storing the data set, on storing very large batches, so which induce an increase in your memory, in the memory that you have to, because you have to store more data, or in this recent method here, where you first compute the embedding by using a first part. So you parse your data set by parsing all your batches and you compute your embedding, and then in a second pass you compute the backward stage and update your gradient later on, and then it induces a large increase in your training time. Okay. So so what do you propose? So we propose this smooth surrogate, and so it's a smooth surrogate which is based on designing an approximation of the rank function. So the average precision here, so you have a given query, and the average precision can be written this way. It's a sum over the positive instance in your data set of the rank of the positive instance divided by the rank of, the rank of each instance k among the positive computed only on the positive over the rank of k among all samples. And okay, and this function can be written this way: rank plus over rank plus rank minus. And so this rank function can be simply rewritten using this Heaviside function based on the similarity between your query and the sample that you consider. And clearly, the non-differentiability of this rank function comes from this Heaviside function, which is the step function. And what we propose is to approximate the step function by a function that looks like this. So a function which has a sigmoid shape here, a sigmoid shape here, and a linear term here. So the point is, so the main objective is that when we design this loss, clearly this loss is an upper bound of the step function, and we choose to only optimize this rank minus function such that when we do that, we by design obtain an upper bound surrogate of the average precision that we get. Okay. And for example, so a strong baseline at that time was to approximate, as it commonly done, approximate this step function by a sigmoid function, as done as shown here. And this is a smooth AP method, but simply replace this sigmoid function, this step function by a sigmoid function. But as you use this, if you use this sigmoid function, then you can show that you don't have an upper bound of your loss because the sigmoid does not upper bound your step function. Okay. And okay, also there was also good gradient behavior of this loss that we studied more in detail. Okay, so this was for the non-differentiability. So we get a nice upper bound surrogate of our loss, and then for the decomposability, So as I was mentioning, what we introduced just to quantify the decomposability is this notion of a decomposability gap. So the decomposability gap is the difference between the average loss that you have when you compute the average loss on your batches and the loss, the least Y loss that you would like to optimize initially. And what we design, what we introduce is this LDG loss, which is a very well-known what we would call what we call a calibration loss, which is simply a pairwise loss that simply imposes the similarity of positive samples to be larger than alpha and the similarity of negative samples to be smaller than beta. It's a very simple loss. But the point is that as this loss is based on this alpha and beta similarity value, which are absolute value and that are shared across batches, it plays the role of calibrating the similarity that are learned across batches. And what we can show is that using these losses, we can show that if you include this loss during your training, you can reduce the decomposability gap that you have. And then you optimize the loss using your batch training scheme that is closer to the loss that you would optimize if you want to introduce this loss. And the good point is that when you do that, also compared to the baseline method, is that it's only a loss that is added during training, and so it does not induce any overhead, neither in terms of memory or training time during inference. Okay, and so we had some comparison. We compare our method compared to this baseline. Smooth AP is really the method based on sigmoid, and other method from state of the art. Okay, so we had good result. Here are the results reported in two standard data sets. So SOP is a data set, a large scale data set of product, and iNaturalist is a data set of natural images. And okay, so we have outperformed this method. And what we can see also is that what is shown here on this right hand side figure is that when we compare our method compared to smooth AP using only what we call this sup AP method, is that when we change the sigmoid by our smooth surrogate, we have consistent improvement in both data sets. And when we add our final method, which is based on adding also this non-decomposability loss, we get improvement. And especially what was interesting is that we get very large improvement in large scale data set in iNaturalist, because we were able to train with small batches or relatively small batches, even when you have very large data set. And in this setting, the loss that you get in your batch is really a very bad approximation of the loss that you would get on the whole data set. Okay, and to finish, I will present an extension of that to deal or to try to control the severity of mistake that we did. So it was really a follow-up of this work. And here, as a motivation, as I was mentioning, so the training of rank loss that I was presenting just before, it was based on binary labels. So we had some binary labels to train our model. We just know, given an image, if an image is similar or dissimilar with respect to the query. So we have this binary label. And for example, this was the introduction slide. If you have, so you train your model on your data set, you have this query image. And if you apply a method that has been trained on binary labels, then you might get this solution, which would be equivalent to, so this bottom solution, which would be equivalent to this top solution. Okay. And what we observe is that, of course, these two solutions, they have the same average precision score, because you have, okay, 4 out of 6 images that are written properly by the model at the same rank. But the error that you make with this baseline solution here, they are much worse than this one, because here you retrieve some images that have nothing to do with the query, here the snake or the butterfly, and in contrast, the top images, you have some errors, but you still retrieve some bare images. So you would like to support more, you would like to train a model which can support the bottom, the output of the bottom list rather than the output of the top list rather than the bottom one. And so to do that, what we include is that we try to generalize this average precision metric by including some prior information. And here what we simply use is to use the relation between the class that we have in our training set as a proxy for measuring the mistake severity that we make. For example, we want to assign a larger mistake severity if we predict a butterfly and that our query image is a bear compared to another instance of bear, but which is still a bear. Okay. And so we use this notion of relevance, which is simply based on computing the hierarchical distance between one sample in the training set and another images in the hierarchical tree that we have. And we we introduce this notion of hierarchical rank that generalize the notion of rank using this relevance function that takes into account the hierarchical information that we have between classes. So basically, that's the main difference that we have here. Instead of having 1 plus a sum of Heaviside function, here we have this relevant function that is taken into account in the computation of the H row. And once we do that, we are able to define in a similar manner this hierarchical average precision metric that involves this H rank function. And that turns out to be a consistent generalization of average precision in the sense that if you replace this relevance function by binary labels, which will be 0 and 1, you come back to the standard AP function. Okay. And so, yeah, that was the final training that we experiment, which was somehow similar to the previous setting I was mentioning. You have your query image, you have your bunch and images, and you have an approximation of the loss function that you have. So you have this sup HAP function, that is the generalization of the AP function in the hierarchical setting. And you have this loss that plays a role of this matrix, this loss function that encourage to have to decrease the decomposability gap that we had before. Okay, and we show that we are better than the baseline. And again, what the most interesting point that we are better than the baseline. We are close to methods that were trained to binary label. So here is an evaluation on the iNaturalist dataset where you have 7 levels of hierarchy. So you have an image. The first level is you want to detect if your image has the same species and so on, up to this 7th level in the hierarchy. And what we observe is that we get similar results when we evaluate our performance for the first level in the hierarchy, but much better results when we evaluate on higher level in the hierarchy. So it directly reflects the fact that we make errors that are more severe in the sense of predicting an image that has nothing to do in terms of class. And finally, I think I'm a bit long, just last thing, we were just trying, so it's an under review paper. We have been introducing a data set. So it's an extension of this GLDV2 data set, which is a large-scale image data set of landmarks. And we release a new data set that has the same images, but that includes some hierarchical information to be able to train some hierarchical model. So that was really to give to the community the opportunity to train your model with hierarchical information and to evaluate it also. Okay, and okay, we have interesting result on that. Okay, thank you. I think I'm going to stop there. So the perspective on both sides for uncertainty at the moment, I'm trying to see for uncertainty, how to define a global measure of uncertainty that can combine the 2 sources of uncertainty I was mentioning, aleatoric and epistemic. Also to see how to apply this framework for a large-scale model and foundation model, multi-modal model, essentially for uncertainty. And for the rest, for the non-smooth and non-decomposable approximation, certainly there are still room for applying this ID beyond rank losses. Okay, thank you for your attention.
Yeah. The next part will be here. Can we consider also other similarities between classes like the word embeddings or the important based here?
Yeah, here it's so in the hierarchy that we have been using, it's based on WordNet actually, because it's in iNaturalist, you know, it's based on a WordNet ontology to build it. Yeah.
Is it possible to extend it to a relation that is not an integer level of
Certainly, you can, so the relevance you can design it. It's up to you. It's because when in the definition of this H rank, you can just change. So it's flexible with respect to the relevance, but what is written here. So if you want to plug any relevance function, you can do it. Yeah.
Well, staying on the same subject, so this is like a training concept. Could you use this at during inference, because you're actually in that area, you know, similarity matchers and image retrieval. There's a lot of like techniques to leverage multiple samples and rankings at test time.
Yeah.
I'm just wondering if that's something that you could leverage or compare to, and but what you're presenting is mostly a training.
Yeah, sure. No, I was thinking because there are all these approach based that are generally called transductive method, where you try to make prediction based on a batch of sample instead of a single one, and that try to leverage the structure in the batch. So here, of course, indeed, here what we do is only in training, and then on the training dot, what we get is only our embedding. So all the knowledge that we get is included in this loss function. It should need some important adaptation, I think, to get something adapted to
Well, I think a similar concept could be applied, you know,
yeah.
Of course, it's not training, but it's still,
yeah,
you know, combining several reference images when you make a decision.
Yeah, the main point is that during inference you don't have any class information, any hierarchical information. You don't have any class, and of course, you don't have any hierarchical information. So you should define a proxy for that. If you
You can measure in certain. Like
Yeah.
you take the top ranks. You know, you could have, for example, if you have one that activates very strongly, but a bunch of them that activate very strongly, but a bit less.
Yeah.
I think you could infer that probably your answer is in the second group, you know.
Okay.
Anyways, that's one.
Yeah.
One thing actually, it's already done quite a bit. I think in surveillance they use that kind of thing a lot.
Okay.
Because anyways, I won't go into other stuff, but
Yep.
I mean the other point that's I mean, you're not dealing with it, but in general there's a big problem with, because the matcher is not learned, right? You're training a backbone. Everyone trains a backbone.
Yeah.
But actually the matcher is deterministic, right? Cosine loss or something like that.
Yeah.
Typically.
Yeah.
So it's kind of a weakness in general with those models, but maybe there's a way of doing some joint training, the backbone and matcher with this kind of concept.
So the backbone and those, sorry?
And the matcher. Like in your image, I think you have like a circle with a plus in it, but that's your matcher, right? You know what I mean? When you're training an image retrieval engine.
Yeah.
It's just the backbone that produces feature representation.
Yeah, and then you have this, in general, this dot product to represent the similarities that you get. But so learning the embedding is used for learning the similarities. Yeah.
I mean, the idea is rough, but there's definitely a way to train, you know, the matcher alongside the backbone.
Okay.
It's a bit more complex. I'm just wondering if there's a concept there that could be developed to do that based on ranking.
I'm not sure. Okay.
Sorry, it's Friday.
That's good.
Yeah.
Any other questions? Yeah, please.
Which of your methods for improved robustness
give us the best robustness runtime ratio.
I don't get your question.
If of your method for improve the robustness,
Yeah,
give us the best robustness ratio
yeah.
runtime. Robustness runtime ratio.
So we here, so in this approach, the point was okay. During inference, so in those approaches, there was essentially any override during in inference time, okay, because everything is done during training. So you just once you do that, you have your embedding, you have your similarities, and there is no override at this time. So there is no really compromise, you know, because we compared to the very naive baseline where you compute the similarity, there is no override at this time.
When you use for quantification the prompt,
Yeah.
you use the static prompt like the human prompt or
Yeah.
the dynamic prompt.
So here the prompt is learned. Okay.
It's dynamic. For each video, you have a specific prompt.
Yeah. Here the point is really for each class. That's for you have a set of prompts that are learned for each class. Okay.
Is the human prompt or
No, it's not. It's not the so the standard clip prompt would be this is an image of this class. And so here we learn all the embeddings. So instead of having this is an image of, we have a given set of local of prompts that are learned during training for each class. And we have a set of local plus global prompts that are learned. Okay, so there is nothing uncrafted here. So all the point is really to learn the prompt.
I have a follow-up.
Yeah.
Based on that.
Yeah.
I like the prompt dropout idea, like the fact that you're generating diversity and feature space.
Yeah.
That's a nice idea.
Yeah.
I'm just wondering though, can you get, because you're not, I guess, necessarily leveraging, I'm just wondering if there's like, because there's a lot of techniques to produce prompts, like text prompts with diversity, right? You could take like a prompt and say it in different ways. And diversity.
Yeah.
I'm just wondering if there was an evaluation to see what approach is better, working at the text level or at the feature level.
Yeah, that's a good point. We did not experiment that at all, but yeah.
It's a question of bird. What produces more diversity?
Yeah. Well, we can still play at the feature level, but still use some approaches to create more explicit diversity. As I think here. Here it was just okay. It was just a way during training to by design enforce some diversity using this prompt, these dropout things. But
I like it.
Yeah.
Okay, well, lucky, I think we do have food outside. Okay. So, thank you again.
Thank you.
Thank you to all of you for attending this remotely. Bye-bye.
Thank you.